So I want you to picture the sheer physical footprint of modern artificial intelligence right now.
Oh, it is absolutely massive.
Right. I mean, we are talking about sprawling data centers the size of actual shopping malls. You've got cooling towers guzzling millions of gallons of water and, entire power grids just strained to their absolute limits just to keep these servers humming.
Yeah, the physical infrastructure alone creates this formidable moat around the industry.
Exactly. Because if you want to build a frontier AI model today, especially an autonomous agent that can, navigate the web and conduct deep multi-step research, the general assumption is that you need an admission ticket to that incredibly exclusive capital-heavy club.
Which means billions of dollars. The prevailing narrative across the tech industry is that training top-tier search agents is no longer a game of clever code. It is entirely a game of sheer industrial scale.
You need thousands of cutting-edge GPUs.
Thousands and massive proprietary data pipelines.
But today, we are looking at a May 2026 technical report from a purely academic team at Shanghai Jiao Tong University. And this report, well, it completely shatters that narrative.
It really does. It's a fundamental shift.
They built an open source model called OpenSeeker v2. And our mission for this deep dive is to explore how this university team bypassed the trillion-dollar infrastructure and built a state-of-the-art AI search agent using a remarkably simple method and a shockingly tiny data set.
Tiny is an understatement, honestly.
We'll get to the numbers in a second because they are wild. But, okay, let's unpack this. Why do we think we need all those massive resources to build smart AI in the first place? Like, what is actually happening inside those data centers?
Right. So to understand their breakthrough, we first have to understand the standard mass production assembly line that the big tech companies use to build these agents.
The Goliath in this scenario.
Yep. Exactly. The industry has basically settled on a highly resource-intensive, multi-stage pipeline. It begins with pre-training on massive corpora, which is essentially feeding the model a significant fraction of the entire internet.
Just scraping everything so it learns human language and basic facts.
Yeah, exactly.
And that part we are all pretty familiar with. I mean, that is how you get a standard large language model.
Right. But from there, the pipeline moves to continual pre-training, or CPT. This is where developers shovel massive, highly specific data sets like terabytes of code or domain-specific research into the model to sharpen its knowledge base.
Okay, so making it an expert.
Yes.
Yeah.
And then comes SFT, supervised fine-tuning. This is where human experts actually write out perfect, step-by-step examples of how a search task should be solved.
Teaching the model by having it mimic flawless behavior.
Precisely.
Which makes sense. I mean, mimicry is how we learn. Show it what to do and it copies you.
Sure, but the industry consensus right now is that SFT is simply not enough for complex reasoning. So they move to the fourth, and definitely the most expensive stage, which is reinforcement learning, or RL.
And this is where the massive compute really comes in, right?
Oh, absolutely. This is a massive automated system of trial and error. The model is turned loose inside a simulated web environment to solve problems over millions of iterations.
Billions.
Yes. It gets mathematically rewarded when it finds the right answer and penalized when it fails or, takes too long.
Setting up those sandbox environments for millions of simulated web searches sounds incredibly computationally expensive.
It's astronomical.
You are essentially paying for millions of server hours just to let the model fail over and over until it finally stumbles onto the right strategy.
Exactly. And that heavy reliance on RL creates a really hard barrier to entry. I mean, it fundamentally locks out the academic community, independent developers, and the open source world from innovating at the cutting edge of AI agents.
Because they just don't have the budget. It feels akin to being told that the only way to build a high-performance fast car is to own a fully automated billion-dollar car manufacturing plant.
Right.
If you just have a garage and a set of tools, you shouldn't even try. But reading this paper, I am left wondering, is all of that automated trial and error actually necessary? Or have the tech giants just normalized this bloated, expensive process because, well, they're the only ones who can afford it?
Well, the researchers at Shanghai Jiao Tong University essentially called their bluff on that exact point.
I love that.
Their premise was that the industry is relying on the brute force of reinforcement learning to compensate for a lack of artisanal, high-quality data. So they developed OpenSeeker v2 by abandoning the assembly line approach altogether.
They just scrapped the most expensive parts entirely.
Completely. Their core hypothesis was that if you feed an AI training trajectories that are of incredibly high structural difficulty and informational richness, a straightforward, supervised fine-tuning approach, that mimicry phase we discussed, is perfectly sufficient.
So no reinforcement learning. No continual pre-training.
None. They stripped the pipeline down to the studs and focused entirely on the craftsmanship of the data.
Let's get into the mechanics of what they actually built then, because the architecture choices are fascinating. They didn't train a new brain from scratch, did they?
No, they built OpenSeeker v2 on top of an existing open-source base model. It's called Qwen3 30B A3B Thinking 2507.
Okay, for you listening, let's break that string of numbers down because it tells a really cool story of extreme efficiency. It's a 30 billion parameter model, right? But it operates on a sparse mixture of experts' architecture.
Yeah, and that architectural detail is crucial for independent developers. In a standard dense model, every single parameter is activated for every single word the AI generates.
Which requires massive memory.
Right, massive memory and computing power.
But this is a mixture of experts. So think of it like a massive research hospital with 30,000 highly specialized doctors on staff. When a patient walks in with a specific ailment, the hospital doesn't page every single doctor in the building.
That would be chaos.
Exactly. They only page the 3,000 specialists whose expertise is relevant to that specific patient.
And that translates to the A3B in the model's name. Out of its 30 billion total parameters, it only activates 3 billion parameters during inference.
Inference meaning the moment it's actually generating a thought or taking an action.
Exactly. So it gives you the broad knowledge base of a massive model with the speed and the low cost of a tiny one.
And alongside that efficiency, it boasts a massive 256,000 token context window. That allows it to hold hundreds of pages of text in its active short-term memory at once.
Yeah, which is essential for web research. And they configured it to allow up to 200 sequential tool calls per search task.
Okay, before we move past those tool calls, we should probably clarify how these search agents operate under the hood.
Right. They use a paradigm called REACT, which stands for reasoning and acting.
React.
Yeah, it is a continuous loop. The model outputs a thought about what it needs to do, then an action, like executing a search query or opening a specific URL. Then it receives an observation, which is just the text on the web page. And then the loop restarts. Thought, action, observation.
So granting it 200 tool calls means giving it an incredibly long runway. It can go through that thought-action-observation loop 200 times before it is forced to give up.
Which allows for incredibly deep, sustained exploration.
But here is the detail in the paper that genuinely made me do a double take. To train this highly efficient model to become state-of-the-art, they didn't use the industry standard of millions of synthetic examples.
Oh, they didn't.
They used a hyper-condensed dataset of merely 10,600 data points, just 10.6K.
What's fascinating here is that volume, or rather, the extreme lack of it, with just over 10,000 examples and a simple supervised fine-tuning process, OpenSeeker v2 achieved parity with, and in some cases totally surpassed, the most expensive corporate models in the world.
It's mind-blowing.
It really is. This is the first time an academic team has produced a top-tier search agent without relying on industrial-scale infrastructure.
Well, if they only used 10,600 examples to train it, the quality of those specific examples must be unparalleled.
It had to be.
We need to look at how they engineered this data because this is the entirely manual, bespoke craftsmanship replacing the automated factory. How do you make such a tiny data set so potent?
Well, the team applied 3 distinct, highly intentional modifications to how they synthesized these training trajectories.
Okay, what were they?
The overarching goal was to force the AI into agonizingly complex cognitive exercises during its training. The first modification involved artificially scaling the graph size of the simulated web environment.
Let's visualize that. What does scaling a topological graph look like when you are actually generating data?
Think about it like this. When you browse the internet, you are navigating a topological graph. A Wikipedia page is a node. The hyperlinks on that page are pathways to other nodes.
Right, makes sense.
In the previous generation of this model, OpenSeeker v1, the synthetic training data was relatively shallow. The AI might start on a node, click one link, find the answer, and complete the task.
So a localized, immediate reward.
Yes. But for version 2, they systematically expanded the size and complexity of that underlying graph during the data generation phase.
Oh, so?
They injected a massive amount of tangential information, dead ends, and just distant sources into the simulation. They structured the data so the target answer was never just one click away.
Oh, I see. It's the difference between taking away an encyclopedia where the answer is neatly indexed and dropping the AI into an unorganized, sprawling library where the clues are scattered across different floors and different books.
That's a perfect way to put it. It structurally mandates that the AI cannot rely on a single source. It must learn to extract a partial clue from node A, synthesize it with a hint from node D, and use that combined knowledge to formulate a search query that leads to node Q.
It builds cognitive stamina.
Exactly.
And that makes the second modification, expanding the tool set, an absolute necessity. I mean, if you are dropping it into a more complex library, it needs better tools to navigate it.
Right. They gave the agent a broader array of programmatic tools to choose from during that React loop. Instead of just basic search and click functions, it learned versatile strategies for querying databases, extracting specific data formats, and navigating really complex site architectures.
But the third modification is where I struggle a bit. They applied a strict, low-step filtering process to the dataset.
Yes, the filtering.
They intentionally threw out any training trajectory that could be solved in too few steps. If a query could be answered with simple keyword matching or a direct, shallow lookup, they completely deleted it from the training data.
They tossed it.
Wait, throwing away correct, verified data goes against everything we have learned about training large language models. I mean, GPT-4 wasn't built by starving it of accurate information. Why would you purposefully delete correct answers from an already tiny data set? It's like throwing away the easy flashcards right before a final exam.
I know, it sounds highly counterproductive. But consider what happens when you feed an autonomous agent a steady diet of easy wins. In machine learning, if a dataset is flooded with one-step or two-step problems, the model's internal weights optimize for brevity.
Okay.
It learns that most problems in the universe can be solved quickly.
So it basically learns to be lazy.
Exactly. It develops a shallow attention span. When it eventually faces a truly difficult multi-hop research task in the real world, it tries 2 or 3 searches, fails to find the immediate answer, and simply gives up or hallucinates a conclusion.
Because sustained effort was never normalized during its training.
Right.
Ah, I see. It lacks the behavioral stamina to keep going.
Yes.
So by dropping the simple queries, they established a minimum difficulty floor.
Yes. Every single one of those 10.6K examples is marathon. The model is exclusively trained on scenarios where the answer is buried deep, requiring dozens of sequential steps to uncover. And we can actually see the mathematical proof of this stamina in the trajectory lengths.
The actual number of steps the agent takes before it concludes a search.
Look at the averages. In the older OpenSeeker v1, the average search trajectory was 46.97 steps. A major corporate competitor, RedSearcher, gives up after an average of only 36.01 steps.
Oh.
But OpenSeeker v2's average trajectory length sits at a staggering 64.67 steps. It is explicitly conditioned to think longer and search deeper.
64 steps for a single query. Let's map that back to the React loop we discussed. That means the model outputs a thought, executes a search, reads the resulting page, realizes it hit a dead end, formulates an entirely new search strategy,
Right.
reads another page, extracts a partial fact, synthesizes it, and it does that 64 times on average. That is an immense amount of sustained focus for an AI.
And because its training data was universally grueling, when you give it a novel problem today, it automatically assumes it needs to run a marathon to solve it.
It doesn't look for the easy way out because, in its learned experience, easy ways out simply do not exist.
Exactly.
Here's where it gets really interesting. We have this hyper-efficient 30 billion parameter-based model. We have a grueling bespoke dataset of 10,600 impossibly hard examples. We have an agent that refuses to give up. The crucial question is, how did this translate to the official industry scoreboards?
Did David actually beat Goliath?
Right. Did this artisanal approach actually beat the mass-produced models from the corporate labs?
Well, the benchmark testing reveals a dramatic shift in the landscape. They evaluated OpenSeeker v2 across several of the most punishing standard benchmarks designed for agentic web navigation and complex reasoning.
I am looking at the score sheets now. Let's break down what these tests actually demand. On BrowseComp, which tests an agent's ability to navigate messy, real-world web interfaces to complete specific tasks, it scored 46.0%.
Which is very high.
And on BrowseComp-ZH, the Chinese language variant, it reached 58.1%.
Right, and those scores reflect a deep understanding of structural web environments, not just text retrieval.
Then there is Humanity's Last Exam, which is a famously brutal benchmark. It is comprised of highly advanced PhD-level questions across dozens of academic disciplines, questions specifically designed to be too difficult for standard AI models to just guess.
Yes.
OpenSeeker v2 scored 34.6%, and on xbench, a rigorous deep search evaluation, it scored an impressive 78.0%.
So to truly grasp the significance of those percentages, we have to look at the models it was competing against.
The corporate giants.
Exactly. Consider Alibaba's Tongyi lab. They built an agent called Tongyi DeepResearch utilizing the full heavy corporate pipeline we outlined earlier. So continual pre-training, supervised fine-tuning, and highly expensive reinforcement learning.
The billion-dollar assembly line.
OpenSeeker v2 decisively dismantled it.
Really?
Yes. On that BrowseComp-ZH benchmark, the academic model beat Alibaba's corporate model by a massive margin of 11.4%.
Wow.
On xbench, it outperformed it by 3%. It also comprehensively outperformed RedNote's proprietary model, RedSearcher.
That is wild. A university team armed with 10,000 highly curated examples and basic supervised fine-tuning outperformed a massive corporate infrastructure utilizing reinforcement learning.
But the comparative performance scale is even higher than that, because OpenSeeker v2 utilizes that sparse mixture of experts architecture, only activating 3 billion parameters at a time. It is a relatively lightweight model, yet it began punching astronomically above its weight class.
Yeah, the paper highlights that this 30B model outperformed massively larger open source Leviathans. It beat DeepSeek v3.1. And for context, DeepSeek v3.1 is a 671 billion parameter model.
That's massive.
A highly efficient 30B model outmaneuvered an agent more than 20 times its size on these specific reasoning tasks. It also bested GLM 4.6, which is sitting at 357 billion parameters.
It even held its own and occasionally surpassed leading closed-source proprietary models like Claude 4.5 Sonnet on these targeted agentic benchmarks.
This forces a total reevaluation of how we measure AI capability. I mean, the industry has been obsessed with parameter count and the sheer scale of the compute budget as the primary indicators of a model's intelligence.
Bigger is better. That was the rule.
But this proves that the internal quality of the reasoning trajectory, the artisanal difficulty of the data you feed the model, can override raw scale. It is the difference between a student who passively skims 1,000 generic textbooks and a student who spends months deeply, agonizingly working through 10 master-level logic puzzles.
Right. The second student develops a far superior capacity for problem solving.
Exactly.
The structural complexity of the training data basically acts as a force multiplier for the underlying parameters.
So what does this all mean? If you are listening to this, why should the methodology of an academic paper from Shanghai Jiao Tong University matter to you?
It's a fair question.
It matters because this team didn't just publish their findings. They open-sourced the OpenSeeker v2 model weights and their training code. They released the blueprint to the public.
It is a massive shift toward decentralization.
They have definitively proven that you do not need a tech giant's mega budget to build world-class autonomous research tools. High-quality, painstakingly curated data is the great equalizer here.
It really is.
And this directly impacts you. If you are an independent developer sitting in your garage or a university researcher with limited funding, you no longer have to wait for Google or OpenAI to grant you API access to a capable agent.
Now, you can build, run, and fine-tune brilliant, specialized AI search agents locally. The barrier to entry has just been radically lowered. It transitions the cutting edge of AI development from a purely capital-intensive arms race into an ingenuity-intensive endeavor. It proves the open source community can compete at the frontier. But, this raises an important question, one that the researchers themselves hinted at in their final analysis.
What is the lingering variable?
They explicitly stated that their bespoke data methodology has not even come close to saturating its scaling potential. They haven't hit the ceiling.
Because they only used 10,600 examples.
Exactly. So consider the implications of this trajectory. If stripping away the easy data and establishing a minimum difficulty floor on merely 10,000 examples was enough to completely bypass the multi-million-dollar reinforcement learning pipelines.
And beat models 20 times their size.
Right. What happens next year? What happens when a decentralized open source community bands together, crowdsources their computational power, and applies this exact same strict difficulty filter to a bespoke dataset of 1 million complex multi-hop examples?
Oh, man.
Could the heavily funded mass production industry recipe that Silicon Valley relies on be rendered entirely obsolete by tomorrow?
It certainly changes how we view that physical infrastructure. The tech giants might still be inside their massive data centers, cooling their thousands of GPUs and paying millions in electricity bills.
Yeah.
But turns out the independent developers never needed to break into those facilities. They just needed to design a smarter, more resilient engine out here in the open.